So hello everyone. As Jennifer said, I'm Marion Zannese, a postdoc at IAS. And today I'm going to present some of my PhD results and more precisely on how we can probe ongoing gas phase chemistry directly from observation. And today is going to be more focused on the organic chemistry with the observation of CH plus and CH3 plus in the Orion Bar. So first of all, typically, when we want to probe astrochemistry from an astrophysical target, we use observations, and then we need to compare it to thermochemical models that, based on their chemical network, can predict the abundances of species and the chemistry. The question I want to answer today is, can we get rid of these thermochemical models and probe astrochemistry directly from observation? And what I'm going to try to convince you today is that we can use formation pumping processes in order to do that. So excitation at formation processes. To study these specific processes, I'm going to use an interstellar laboratory, the Orion Bar, which is located in the Orion Nebula. So it is the bear-shaped structure that you can see in the middle of the circle there. And it is highly irradiated by the trapezium cluster that we can see in the center of the image there. I insist on the term interstellar laboratory because everything that I'm going to present in this talk could be applied to other astrophysical environments if they have similar physical conditions. So this region has been observed by the James Webb Space Telescope in September 2022 by the ERAS program PDS for All. And the NIRCam imager has given us very spectacular images of this region with very high spatial resolution. With this program, we also have spectroscopic data in a smaller field of view here. The geometry of the Orion Bar is very nice because as it is edged on, we can see all the very specific region of the photodissociation region. Indeed, the Orion Bar is irradiated by the trapezium cluster, which is here in the upper right side of the image. And near the star, the UV field is intense enough to ionize almost all the species around. So we are in what we call the ionized region that we see here in blue. When we go deeper into the cloud, the UV field is getting extincted by dust and gas. So we cross what we call an ionization front. And then behind it, atoms are able to survive this UV field. And we are what we call in atomic region that we can see here in red. Further, again, into the cloud, the UV field is extincted enough for molecules to survive, and we cross what we call dissociation front, where the atomic hydrogen becomes molecular. So with the spectral imaging of the James Webb Space Telescope, we have access to spectra all over these regions. And more fantastically, we also have access to a protoplanetary disk, which is a smaller object that is also irradiated by the trapezium cluster. So we don't really probe the disk, but more a photo-evaporated wind that is getting depleted of the disk due to this intense UV field. In this region, we observe very, very rich spectrum with a bunch of H2 lines, some very prominent aromatic bands. But what was more spectacular about this data is that we detected a lot of very excited molecular lines that are very tiny. We can't even see them if we look at the whole spectrum, but hide a lot of physics inside them. For example, in DT03506, which is the protoplanetary disk in our observation, if we focus on the region around 3 microns, we can see a spectrum of low vibrational emission of OH that is very, very excited. This emission cannot be explained by typical excitation processes such as collisions or radiative pumping. So when we heard about the work that was done in Salamanca and Madrid about chemical pumping of OH, we wondered if it was what could explain the spectra that we were observing. So chemical pumping is the process where when OH is formed by this formation reaction in the gas phase by atomic oxygen and dihydrogen is being formed already excited here in a vibrational state. The level that are populated by this process depends on several aspects. The temperature, but also the population of the H2 levels, because the internal energy of H2 could be used to excite the OH that is produced from this reaction. Right after being formed, OH directly de-excites through the low vibrational transition that we are observing. Thanks to the state-to-state rate coefficient that were calculated in Madrid and Salamanca, we were able to nicely reproduce the spectrum that were observed in TO3506 with a chemical pumping model taking into account everything. What we realized is that the gas phase oxygen chemistry that we probed in this observation is very similar to the gas phase carbon chemistry. Indeed, both of this chemistry relies on reaction with excited H2. So what I wondered in my work is that as we have proven that chemical pumping could be interesting in the formation of OH, could it also be interesting in the carbon chemistry? Indeed, in the Orion Bar, we detect two molecules of these carbon gas phase reactions, CH plus and CH3 plus. Similarly to OH, CH plus is detected in the disk. So here you have a map of an excited line of H2. The trapezium cluster is on the left, and the UV field is getting extended from left to right. So you can see the disk here and the three dissociation fronts that we have in our data here. So similarly to OH, CH plus is also detected in the disk, but it is contrary to OH, it's also detected in the three dissociation fronts. The fact that we detect CH plus in various environments of the Orion bar makes it possible to study the spatial distribution of its emission. So we can notice that in the disk, the emission of CH plus seems to originate from the same region as excited H2. And we have exactly the same result in the dissociation front, where we see that CH plus, that here is in blue, peaks at each dissociation front exactly like excited H2. So these results are in agreement with the fact that CH plus is formed in the gas phase by reaction from C plus H2, which was predicted by thermochemical models. The issue is that studying only the spatial distribution of its emission cannot explain how it's excited and what excite the levels that we are observing. So to understand that, I studied the excitation of CH plus in both of environments, in the disk and in the PDR. And we have some very nice results. First is that in the disk, the excitation diagram of CH plus shows that the excitation temperature of the vibrational levels of CH plus that we are observing have about the same is about the gas temperature. We have an excitation temperature about 900 Kelvin, which is similar to the gas temperature. However, we can see that a single Boltzmann distribution cannot account for both V1 and V2. V2 seems overpopulated in comparison to V1. In the PDR, we also have some very interesting results, but also very different. We can see that in the V1, the levels are probed by James Webb in the three dissociation fronts. The excitation temperature of these levels is very, very high, 100 and 500 Kelvin, which is a lot higher than the gas temperature in this region, which is around 600 Kelvins. And it's also a lot higher than the excitation temperature that we get from purely rotational lines of CH plus that were detected with Herschel. So that's pretty counterintuitive results, because it means that in the PDR, CH plus seems more excited, even though the PDR is colder than the disk. So these results show that clearly the excitation of CH plus is non-LTE. Could chemical pumping also explain the observation that we have of CH plus similarly to OH? So I remind you, the levels that are populated after chemical pumping depends on several parameters: the temperature, the population levels of H2, and the state-to-state rate coefficient. Once again, we have all the information we need to model this process. Indeed, the state-to-state rate coefficient were calculated in Madrid and Grenoble a few years ago, and the observation of the many, many lines of H2 in the James Webb data makes it possible to have access to the gas temperature and the population levels of H2. And the first thing we remark is that in both this region, we have very different gas temperature and consequently a very different population of the H2 levels. So when we take into account these parameters in an analytical models of chemical pumping, we can nicely reproduce the observed lines of CH plus both in the disk and in the PDR. And what the very counterintuitive result that we had before, but the fact that we have a higher excitation of CH plus in a cooler gas is naturally explained by chemical pumping, because the gas temperature and the H2 level population is different in both environments. As CH plus directly de-excite after being formed, the intensity of the lines that we are observing in this region are directly proportional to the formation rate of the molecules, meaning they are proportional to the number of CH+ formed by unit of time. That means that directly from the intensity that we observed, we can derive the chemistry that is happening of the carbon chemistry. We can derive the formation rate of CH+ in the disk and in the PDR. And we can already notice that the formation rate of CH+ is much more higher, 10 times higher in the disk than in the PDR. The formation rate depends on several parameters, and as it is a two-body reaction, it depends greatly on gas density. And the other parameters are measured parameters. The the state-to-state coefficient were calculated, and the quantity of H2 and CH+ can be measured from observations. So thanks to the derived formation rate from the observation, we can derive a local gas density, a quantity that is often very difficult to measure. And that is some very excellent result, because in the disk, we estimate that the gas density is around 10 to the 7 particle per centimeter cube. And that is extremely satisfying because it is consistent with other traces. We derived the same density with the chemical pumping of OH that I presented it earlier, but also with another diagnostic that were made from H2 lines compared to some PDR models from the Meudon PDR code. In the Orion bar, we derived a lower density, about 10 times lower, which is also consistent with other traces, the fact that the Orion bar is less dense than the disk. In the Orion bar, I told you before, we also detect CH3+. It was first detected in the disk, and in my work, I've shown that it is also detected in the 3 dissociation fronts in the Orion bar. What I'm trying to do is study this observation in light of CH+ and H2, because thermochemical model predicts that it is formed in the gas phase. And we have actually some very interesting results, because CH3+ is also detected in the same region of CH+, in the disk and the 3 dissociation front. So it means that it is detected where H2 is bright. And what is even more fantastic, it is also very similar in excitation, meaning that once again, the excitation of CH3+ is higher in the PDR, with an excitation temperature about 1200 Kelvin, than in the disk, which is about the gas temperature. So we also have the result that there is an higher excitation of CH3+ in a cooler gas. The question I have in mind is, can chemical pumping explain the excitation of CH3+? And unfortunately, that's a question I cannot answer, because contrary to CH+, we do not have the molecular data from the state-to-state coefficient rate from one level of H2 to one level of CH3+. So I believe this is really a new system that needs to be studied by molecular physicists, because as it was already mentioned in other talks this week, CH3+ is expected to be the origin of multiple hydrocarbons that are found in the gas phase. So if we want to understand the carbon chemistry in the interstellar medium, it's really important to understand how CH3+ is formed and how it is excited. So I'm going to leave you with this take-home message slide. I hope today I convinced you that formation pumping processes, such as chemical pumping, can be used to probe astrochemistry in action directly from observation without having the need to use complex thermochemical models. They are strong and robust diagnostic. We can derive directly from intensity, line intensity, the formation rate, but also the local gas density. And with the James Webb Space Telescope, we expect that more and more small hydrates, very excited hydrates, are going to be detected in various astrophysical objects with similar conditions. So protostars, protoplanetary disk, PDRs, comets. So I think it is really important to insist on how the collaboration with molecular physicists is vital in the James Webb era to make use of these specific processes that are very useful to probe the interstellar medium. And on this beautiful conclusion, I thank you for your attention.
Thank you very much. Do we have any questions?
Thank you for your presentation. So I was wondering, maybe it's completely stupid, but what about CH2 plus?
Yeah,
I mean,
that's
because I guess it should emit in the same region.
So it's a very good question, why we do not detect CH2 plus in the data. And that's actually a question we are working on with some spectroscopists at ISMO. The thing is that in the data, we don't think we detect CH2 plus because most of the lines in the Orion bar that are detected were assigned. There's a couple that are still unidentified, but very, very few. So we are trying to understand why we detect CH2 plus quite nicely and why we detect CH3 plus quite nicely also, but not CH2 plus. And the thing is that the spectroscopic data of CH2 plus is still not quite done. So we don't really know how the spectrum of CH2 plus look like. And we have some ideas for why is it not detected, but it's still very preliminary results because we need to do the spectroscopic, the spectroscopy of CH2 plus before. So we think it's because if CH2 plus is excited, it might be de-exciting through very, very various lines. So it could be diluted into the spectrum, and so not having lines intense enough for us to detect. But that's still some hypothesis because we need, there's a work before that needs to be done and is being done actually.